Hello everyone. Today we'll be looking at complex vector spaces. Before I talk about these vector spaces, which are complex in nature, we are going to do a little review of complex number systems. So what is a complex number? A complex number is given by the expression a plus by, where a and b are real numbers and I is given by square root of minus 1. So there are specific things. A is called the real part of the complex number and B is called the imaginary part of the complex number. So these complex numbers, guys, remember they came into existence because we never had the scenario of a square root of a negative number. So that's where complex numbers came into being. Okay, let's look at some of operations on the complex numbers. If I have two complex numbers, and alpha is a scalar, can be real, then when you add two complex numbers, that means you say u is a1 plus b1i, v is a2 plus b2i, then adding two complex numbers is like a1 plus b1i plus a2 plus b2i is basically adding the variables with the same like terms. So b1i and b2i will be gathered together, and a1 and a2 who do not have the I, they're not gathered together. And u minus v, the difference of two complex numbers, is similarly the same as we normally do. You have a1 plus b1i negative a2 plus b2i. So basically you gather the like terms, which is a1 minus a2 plus b1 minus b2i. Now if you're multiplying by a scalar, and it's a real number, so alpha times a1 plus b1i is basically you're distributing the alpha inside. Okay, that's simple. It's very simple to have sum, difference, and scalar multiplication of two complex numbers. Let's talk about multiplication of two complex numbers. Okay, if I have two complex numbers u and v, say a1 plus b1i, and I'm going to do it with the product with v, which is a2 plus b2i. So basically just doing normal multiplication of like polynomials. The only thing now is you will have to make sure when the I pops in. So it's like a1 with a2, then a1 with b2i, b1 with a2i, and then b1 and b2, then I with an I. That makes it I square. Remember, these are, think of these are like the simple variables. Okay, so I with an I makes it I square. Now, remember the most important thing, that I is square root of minus 1. So I square would be, like you square this, is minus 1. And I cube is minus I4 is I. So in the complex world, wherever you see I, you just basically go between these four values. I, minus 1, minus I, and 1. Okay, let's come back to the problem. So we have a1, a2, and b1, b2 I square. Now this I square becomes minus 1. So now it is a constant. Whereas the I terms, which are in the middle of these two, they're gathered together and they give the last two terms in the third equal sign. So here you have a1, b2 plus a2, b1. You put them in parentheses with an I. And then you get the constant terms together and you get a1, a2 minus b1, b2 and plus the same. So that's how you multiply two complex numbers. There's one important concept in complex numbers. It's called conjugate of a complex number. Conjugate of a complex number has a very powerful role to play. It says that if we have a complex number, say a plus bi, and let's call it z. Z is a very conventional term we use in mathematics. Then the complex conjugate of z is denoted by a z bar, which is given by a minus bi. In other words, when you're given a complex number, its conjugate will have negative sign of the original of the one which has an I next to it. So suppose if my complex number was 3 plus 4i. So its complex conjugate z bar would be 3 minus 4i. On the other hand, if I had a complex number z, that doesn't need a bar on the front. Okay, so if I have z1 equals minus, say 4 minus 3i, then z1 bar, the complex conjugate, would be 4 plus 3i. It's basically you change the sign in front of the I expression. Okay, so it's a very important property of a complex conjugate, and that is when you multiply a complex with its conjugate, you always get a real number. So let's do the multiplication z with z bar. It's a plus ib times a minus ib. It's like difference of squares. So it's basically a square minus b square I square. Now I square is minus 1. So what happens is when you're multiplying a complex with its conjugate, you actually get a real number. Okay, now let's talk about division of complex numbers. So if you have two complex numbers, the division, say u over v, is also a complex number. But we would like to write it in a proper format like x plus iy. Okay, so let's see how to do it. We're going to use it with the help of an example. If my u is 2 minus I, my v is 3 plus I. So u over v is 2 minus I over 3 plus I. Now, this expression does not look like this. In other words, I want a real part of the complex on its own and the imaginary part on its own. But at this point, it's all messed up. So what we do over here is we try to do some manipulations. And the way to do it is you look at the term which is in the denominator and you multiply by its conjugate. So if it's 3 plus I, you're going to multiply by 3 minus I. And that's what you divide and multiply to, because remember, the original problem cannot be changed. Okay, then after that is a simple multiplication of numbers, of complex numbers in the numerator, multiplication of complex numbers in the denominator. Okay, so let it go. So let's look at these numbers. So when you do all the math, we get a 6 minus 5i plus 1 over 10. Now get the complex numbers together. So this is what you see. A 7 minus 5i over 10. Now remember, you have to separate them as x plus iy. So my x here is 7 over 10. My y is minus 5 over 10. So these two complex numbers, when you are looking in the forms of a division, actually looks like this. So this was a brief recap or a review of our complex number systems. Now we go to the main part. Relate these complex numbers to the vector spaces. Okay, here we go. A complex vector space. A complex vector space consists of a set of vectors together with operations of addition and scalar multiplication on the vectors that satisfy the 10 axioms as was given in the definition of vector space in section 4.1. The only difference here, guys, is, that the vectors and the scalars are all complex numbers. That's the only difference between a complex vector space and a normal real vector space. Everything else is very similar. So we say Cn is a complex vector space where vectors in Cn are of the form u1, u2, un, and all the ui's are complex numbers. The operations of addition and scalar multiplication is defined as follows. If U is a vector, an element of Cn, that means it's an n-ordered tuple, think of that, U1 to U1 and V1 to Vn, all of these are complex numbers. And my alpha, which is we needed for our scalar multiplication, is also a complex number. So when you add these two complex numbers, you're getting U1 plus V1, comma, U2 plus V2, dot, 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 Un plus Vn. And when you multiply alpha with a complex number, alpha is complex, this is also complex, guys. So everything is a complex over here. So it's basically you are distributing alpha inside each of these terms of the U vector. Okay, let's do some little computation to see what we are talking about. Now, I have two complex numbers, 2 plus I, 3 minus 4i, V, 1 minus 3i, and 5 plus 3i. So if I want to add two complex numbers, is basically you will add the first with the first component and the second with the second component of v. Second component of u will be added to the second component of v. And then you simply do addition of like terms on both the sides, and your final answer comes out to be minus 2i plus 3 and 8 minus i. Now that's simple. When you add complex or subtract complex numbers, it's not a problem, even if you are in the, so here we are in C2 world. But if I multiply a complex number to a complex number, that means scalar multiplication, that's where you're going to be a little careful, because you see now my alpha is a complex number and I'm multiplying to a complex number which is in u is in C2. So when you're multiplying, remember you're distributing this alpha to both the terms inside u. So you're getting 4 plus 3i times 2 plus i, 4 plus 3i times 3 minus 4i. And then what is basically happening is multiplication of two complex numbers. And when you do the math, remember there's going to be an I squared somewhere. Remember to change the I squared to minus 1. Keep that handy, guys. I squared should be equal to minus 1. Okay, so okay. Seems my hand is not kind of steady here. Minus 1. Okay, fine. Now I'm happy here. So when you do all the math, we get another complex number. The most important thing for us is how can we find the dimensions, how can we find basis set and all those things. Here, so many of the properties of this Rn are very much shared by the complex CNs. For instance, scalar multiplication identity is the scalar 1 for Cn, and the additive identity is the 0 vector. The standard basis for Cn is the same as for Rn. E1 is 1, 0, 0, 0, E2 is 0, 1, 0, 0, 0, and En is 0, 0, 0, 0, 1. The dimension of Cn is the same as dimension of Rn, which is an n. So this was just a little concepts related to our complex vector spaces. Now let's go ahead and do an example to prove that this is a basis. So we would like to show that the set I, which consists of complex numbers, is a basis for C3. Now C3, remember, I should have three components of vector in C3. So 3 rows, I, 0, 0. Just making my life simple, we could have written as I, 0, 0 also. But just to make my life simple and save some space, I'm going to use it like a row vector. Now, dimension of C3 we already know is 3 from our previous slide. Now, we want to prove that it is a basis for C3. Remember, in our section 4.5, we learned that if we know the dimension of a vector space, and we have a set which has exactly the same elements, that same number of elements, and if we can prove that that set is linearly independent, then it becomes a basis. We don't have to prove that it is a spanning and all those things. So the main thing is to prove it is linearly independent. So go back to the definition of meaning of linear independence. That means if you take a linear combination C1, V1, C2, V2, C3, V3, where these are scalars, such that when you take the linear combination with these vectors V1, V2, V3, so I'm taking this to be V1, V2, V3, then the only way this equation would be linearly independent if each of the CIs is 0 only. So after that, guys, what you have to do is just do simple math. Plug in the value C1i 0, 0, 0, C2 0, 0, I, C3 0, 0, 1. Now remember, this is a vector, 0 vector, because all the elements are in C3. And then by equality of, these vectors, C1 of I, C1 is 0, C2 is 0, C3 is 0. And hence, this little set is linearly independent and it becomes a basis for C3.